Good morning, everyone. Let's get started. Thanks for coming to today's workshop about the equatorial ionization anomaly and the ionospheric irregularities. And we have a total of 16 fantastic presentations today, and I hope that we can stick to the schedule. Otherwise, this session will run until the banquet. And okay, so our first speaker is Cesar Valadares, and his talk about multi-year statistics of TEC depletion and TIDs in the American sector. You can use the laser point here.
Yeah. How do we advance? Just with this?
Yeah, you can either use this or use this.
Yeah, okay. Good morning. My name is Cesar Valadares. I'm going to be talking today only about the TEC depletions, just because of the constraints in the time. I selected only one topic. These TEC depletions are actually the equatorial plasma bubbles, spread F, the range type. Yeah, so I've done some statistics, but first let me mention what we have done in this slide. Here I presenting the trend in TEC values for 25 stations. And you can see these yellow traces going obliquely. It's because these bubbles are drifting eastward. And the 25 stations are arranged according to the longitude, so I can see the progression of this. Yeah, this is the purpose. I can discuss more about the methodology to detect, or the trend these bubbles. Is not that simple. Yeah, but it's sort of long to discuss how I do it. But the real effort is to try to correlate and compute the velocity and correlate with scintillations. That was the purpose. This is, of course, is part of LISTEN, and we calculate TEC from all these red dots that you see, almost 800 stations. And the blue ones, which are close to the magnetic equator, are the ones that are projected there, only for one PRN, which is 18, I believe. Okay, so we do this for many years. We started in 2008. We are now processing until 2020, so it's more than a solar cycle. And these are the statistics. You see on the right, on the left side, the TEC depletions for 3 years. On red are the statistics for Peru, which is on the west coast of South America, and the other is Brazil, which is in the east coast of South America. You may say that this is only 45 degrees difference in longitude, but no, the statistics are quite different. And you can see, if you look carefully, the local time extension of this is much longer, sometimes in Peru, and that varies. In solar max year, for example, 2013, you can see that in Brazil, you see almost all the time between October and March. So it's almost 100% probability of occurrence, which means it's very easy to predict. At the contrary, in the Peruvian sector, in red, you can see that it's only 70 or 75% occurrence, much different. So the physics changes between 45 degrees longitude. And also it changes when you go to other years, and you can see how it changes, how decreases the amount of scintillations that we see. By the way, each of these days has been processed separated individually and then put here in these statistics. When we go to 2019 at the bottom, you see that there is almost no scintillations. And that becomes also easier to predict in Peru in some way, because most of the time there is not going to be bubbles or a spread F, but it becomes more difficult also at the same time. But this duality of this is the statistics in Brazil, of course, diminished. Now, on the right side of the figure, you see the velocities. And this is how the depletions move. It's not the zonal drift of the plasma, it's the bubble, which is a little different because we compare with Jicamarca. zonal winds measured by the radar. And there are 10 or 20 meters difference. And we know why. But anyway, this is very useful in the sense that if we know that the bubbles are here in Peru, we know later how much time it's going to take to go to Brazil and see there. We are always working on categorizing how this drift changed, and also how the depth of this depletion changes, and how the scintillation changes in time going from Peru to Brazil. If you look carefully, you are going to see that in Brazil, there are times when the velocity becomes green, which means going westward. So it's a reversal of the velocity. What happens? We believe that is the drift or the plasma that is in the westward direction, and the bubbles start moving west. And I've seen cases, no, of course I'm not presenting here all individual cases that show that, but in the paper, I think there is one figure that. Now, I'm going to switch gears a little bit, no, and go to the other project. So you know the spread F, no, is due to the bubbles, and that's, hold on, yeah, that's okay. And that's mainly due to this relative instability that moves the plasma up, and it starts occurring the bubble and also all this structure inside the bubbles that come. So we decided to test the hypothesis that is the vertical drift, the one that controls the initiation of the bubbles. How well does it happen? If you see this red line on the left side, in the upper left plot, you are going to see that corresponds to 19. Well, there is a PRE here on this day, but there is no bubbles. And you can see it also on the left side plots, no UHF scintillations, no L-band scintillations in 3 stations in Peru. And even if you look carefully to the plot in the middle, there is no bubbles. Each of these red, blue and green traces is a bubble that was detected by our program. But in the Peruvian sector, there was nothing. This is more or less typical. It happens a lot of time. No, 20, 30% of the time. There is nothing in Peru. There's a lot of stuff on the east side of South America. No? Fortunately, we have also the TEC latitudinal profiles. And that's what I'm plotting here on the right side. There are 4 longitude sectors. And you can see all these latitudinal TEC profiles. No? And if you look more or less at the middle and also on the west side of South America, you see a single peak. And this is the anomaly, very asymmetric, that is due to these meridional winds. And I believe it's the meridional winds, which are very strong on the west side, but not so strong on the east side, which has stabilized the relative instability and inhibited the growth of the plasma bubbles. This is another case that exactly shows the same. No scintillation whatsoever in Peru. This is very close to South America. And then go to my conclusions. Yeah. This is the PRE when it's more than 30 meters, which should destabilize the relative, but is stabilized by the meridional wind. Yeah. Thank you.
All right, thank you. So maybe due to the time conflict, we just proceed to the next speaker.
Okay. Our next speaker is Dr. Edavoki Izenga from Aerospace.
I will remind you at 5 minutes. Okay. Yeah, 5 minutes. I think that's a good one to say. Okay, I'm going to show you the impact of the quiet time. So just to go to the conclusion. So this is what you can see, the traffic light operation map. That's for the users who would like to have. So on the left, you can see that's on the storm time, which is the Gagan storm. May 2024, or I think it's October actually, October 2024. On the left side is a quiet time, absolutely quiet time when KP was less than 2. And the top panel is from GPS L-band scintillation, and the middle one is from in situ measurement, and the bottom one is ROTI. So what we did is the bubbles are field aligned. So whenever you see a bubble or scintillation, then we highlight it along the field line. So red is do not operate, and yellow is and caution, green is go. And that's what they wanted to have it in our model in the future. So the question is, you can see between the storm time and quiet time, the quiet time is almost every day. A huge swath of longitude was covered, which are not safe to operate VHF and L-band frequency in that region. So that is the idea. What is driving the mechanism? So until now, we know there is no vertical drift, no scintillation, or no bubbles, so you are safe to operate. But sometimes it's not the case. Here, what you see on the top plot is a contour map, that is a ROT map. On the middle one, you can see VHF S4 index, which is scintillation, and then the bottom is drift. The drift, as you can see, sometimes it is reversed on both cases, but there is scintillation, and there is also ROTI. ROTI is a kind of big regularity. It's not on a Vernier scale regularity, which is less than a kilometer. But whenever ROTI is highlighted up, I mean, that gives you a good warning whether there is scintillation or not. We can also see it from in situ measurement. You can see one of the cosmic satellite. On the top is the pass, the ground pass highlighted. The bolded one is actually wherever there is a scintillation or irregularity activity. And then the bottom one, you can see the density, and then we actually convert that density regularity into index, which is small scale and large scale index. So from now on, what I wanted to show you is a small scale index instead of showing you the irregularity, and highlighted where the satellite is coming up. Here is a movie, just I think a couple of days movie. This is about 3 or 4 independent observation. You can see GPS, you can see in situ, you can see also gold. Gold, whenever it is available in that field of view, you can see those stars which is jumping back and forth on the top plot. That's from in situ measurement, highlighted with the in situ measurement as well. So what is the driver? So here is the equation, since I don't have the time, but I wanted to show you on the right bottom, that is a statistics showing you the S4 index as a function of drift velocity. So you can see the blue is, I think, that satisfy the current understanding. Whenever there is drift velocity greater than at least 10 meters per second, you can have bubbles or scintillation, that's okay. But the black dots are actually between 0 and 10, which is not possible to have a drift according to the current understanding or according to that equation there. The red is even the worst. You can have S4 up to, I don't know, 0.8 or more, but the drift is reversed into negative. So that's a thing. So we also look at it just a correlation with gold measurement in the middle. The top one in the middle is the temperature, and the bottom in the middle is actually the radiance. You can see the gravity wave structure on the American sector. At the same time, ROTI is highlighted significantly, and the left is before the gold measurement, and the right one is after the gold measurement. In both cases, you can see a lot of regularity going on. I didn't show here drift because we didn't have one there, but there are cases. So we wanted to understand what is the driver mechanism. So we came up, I think this could be due to the forcing from below. That's the gravity wave structure. So what you can see on the top is the time satellites passing through, and the red dot is where we have VHF. And you can see that from the temperature oscillation, you can extract the gravity wave structure at the bottom, plotted altitude as a function of latitude. And on the right, the same thing, but at different longitude. You can see a longitudinal difference is also controlled, seems to be controlled by this forcing from below. Now, the one that I showed you is actually from low latitude region. The one that I'm showing you is mid-latitude region, and that is also absolutely quite high. And the one on the left is Boston, it's Boston, and then in the middle, somewhere to the west, and then go to the west. So you can see these bubbles, or blobs of bubbles are actually moving to the west. What you see over here on the top is actually the ray path, and then the satellite track highlighted or color-coded with elevation angle. And the bottom, the middle two is the signal-to-noise ratio for L1 and L2. At the bottom one is S4. So if I show you without color coding, this might be multipath. No, it is not multipath. It's actually, the elevation is almost 90 degrees there, but you can see a real scintillation going on. That is on the mid-latitude, which is actually crazy. And at the same time, we saw from NOAA, there was actually a tropical storm going around that area, and at the same time, GOES was actually taking an image, infrared image, the gravity wave structure going on. So we took 2 passes here, I'm just going fast, for SABR measurement from time satellite. So the top one, where that tropical storm is rotating around, you see the gravity wave structure is very much enhanced, but on the other side, there is also gravity wave. So it looks like this wave is moving to the west at the same time, creating, Parkinson instability and create that irregularity. That could be the reason, I think. So this is good to go, actually, but we need a modeler. So the one I highlighted in green is actually, we are going to do the coordinated observation and modelers. We give modelers to show us how the gravity is propagating up, and we get another modelers from the ionosphere, try to take that gravity wave and adjust it and reproduce the irregularities that we saw. So I think that's what I have.
Thank you very much. Yeah. All right. All right, due to the time conflict, let's just proceed to the next speaker.
Okay, let me time myself. Okay, good morning, everyone. Today I will briefly show some cryo-time super-equatorial plasma bubbles in the South America and some very preliminary statistical results. Okay, here is just some arbitrary definition of the super-equatorial bubble. You can see this is this depletion is the superplasma bubble we are talking about, and here I give some arbitrary definition. First, it should be ideally in the meridional direction, and the depletion should extend beyond certain magnetic latitude, and the depletion should also be deep enough. Here I choose 20% to differentiate from the TIDs. And in the literature, there are many studies showing that those super-equatorial plasma bubbles can develop during the storm time. Recent years, almost every superstorm or intense storm has super plasma bubbles. But how about, as Dr. Adovaki and shows that during the cryo time, there are also some scintillations, and there are some super plasma bubble associated with them. And here I use some simple algorithm and try to figure out whether there are cryo-time super-equatorial plasma bubble in the South America, because it's at the very right location to observe those bubbles around certain magnetic latitude. And here, this is some algorithm. We grade the TC at those specified magnetic latitude and then do some smooth and detrend and to find out the valid signal in the TC. And here you can see this is the very clear depletion at a certain south latitude. And here is the associated TC map. This is in the geographic coordinate, and this is converted to the geomagnetic coordinate. Okay, and here is some very preliminary statistical results in 2024 in the South American sector. And here the orange color means the cryo-time superplasma bubbles, and the blue one shows the storm time plasma bubbles. And here I use a night to, here we count the nights. For example, if during one night we can see the superplasma bubbles, we will count one. And you can see there is a total of about 30 to 40 nights we can see the superplasma bubbles, then it's 10% of the total year. And you can also see there is a big discrepancy between the storm time behavior and the cloud time behavior. During the storm time, it's the majority of the storm occurs during the around the summer. In May, there is a big storm, and in October, in November, they are all big storms. But during the cloud time, you can see they prefer the local summertime. And this is very consistent with the climatology of the equatorial plasma bubbles in the South America. This is because the South America has a very large declination angle, and during the local summer, the terminator and the magnetic field line is almost parallel, so they can support the strongest plasma bubble development. But for the mechanism, I think this is a very wide open question, and I have heard many talks about the day-to-day variability of the PRE. That is definitely one potential. Someday we have very strong PRE and very strong ERA, and maybe we can have the superplasma bubble. And also, as Dr. Isengel mentioned, the gravity wave, if we have very strong perturbation from the lower atmosphere, maybe we can also have some superplasma bubbles in the mid-latitude region. Okay, that's all I want to talk today, and I'm open to questions.
Any questions? So, yeah, go ahead. Probably just shout out.
Have you considered also the size of the seeds? I mean, why you have these super bubbles in the summertime but not in the other seasons? For example, do you have TIDs, gravity waves, during that night?
Sorry, we haven't checked yet, but our explanation for the local summer preference is the Trinidad theory, like the angle between the terminator and the geomagnetic field line.
Okay. Any other questions? All right. If not, let's just proceed to the next speaker. Okay. Where is the speaker? Okay, go ahead.
Out of curiosity, have you taken into account substorms?
No, that's maybe something we should check. Maybe the substorm can also give you some PRE. Yeah, that's a very good point. Thank you.
All right. Thank you for the speaker. Let's proceed to the next speaker.
Okay, our next speaker is Eunice Santos from UT Dallas.
All right, go ahead.
Yes.
So good morning to everyone. So I'll try to be short. The motivation for this work I'll be presenting today is to understand the extent to which contributions from mild geomagnetic storms can transition the ionosphere from a non-EPB to an EPB state. We already have people looking at big storms. I'm looking at mild storms. We also want to understand under which seasonal conditions the equatorial ionosphere is more sensitive to those mild contributions, and desirably to learn a little bit about the levels that are required for that transition. So I will jump directly to the results. So basically what I did, I used some gold data that was available, and I classified the nights as EPB or non-EPB nights. That's what you were seeing in this bar plot. Red means EPB, green no EPB. It is divided by season and also divided by geomagnetic activity. So as you look from left to right, that means the geomagnetic activity is increasing. So during December solstice, you can see that we have larger occurrence of EPB nights, which is expected. However, that doesn't change much with increasing geomagnetic activity. For equinox, you can see that if you look at the yellow arrow, this is the arrow is highlighting the trend. If you look at the equinox, the trend increases a little bit, but definitely on June solstice, you can see that the trend is there. So as we increase the geomagnetic activity, we have more and more occurrences of equatorial plasma bubbles. And the sharpest increase happens when we change from quiet to mild geomagnetic activity. We also looked into what I'm calling facilitating processes, more specifically in the vertical drifts, because the vertical drifts are a sine qua non condition for the initiation of EPBs, and they are also impacted by penetration electric fields whenever we have geomagnetic activity in these early nighttime hours. So we use Hikamarka data, and you can see that the trends are kind of similar. During December solstice, we don't see big changes. In the equinox, we see a little bit of change, maybe a little bit of increase if we consider the median absolute deviation here described by this gray area. But during the June solstice, we have the same trend again. Perhaps more importantly, if you look at the mild to moderate conditions is the middle bar in June solstice, we start reaching the values that are typically referred as the ones required for EPB generation. So even though the contribution can be subtle, but that can be crucial for the initiation of EPBs. Of course, when we look at this data, these observations, we have plenty of things happening. We have this convolution of things. One way we can evaluate unambiguously what's happening is by using numerical simulation. And that's what I did. So I use realistic vertical drift profiles extracted from Digizone data in the Brazilian region, and I ingested those profiles in Summitry to see if we would see any difference. I was able to find 2 nights for this first case study in which in one night we didn't have geomagnetic activity, and in the other night we had a very mild geomagnetic activity. So in June 24, the geomagnetic activity was very mild, and in June 25, it was quiet. So even though the contribution was very mild, that added a little bit of upward drifts in the early night time and changed completely the environment. And in the middle panels, we are seeing real observations of scintillation. During that mild geomagnetic activity, we had scintillation reaching 0.7 in terms of S4 amplitude scintillation. And in the next night, without any geomagnetic activity, no scintillation at all. Interestingly enough, when we look at the latitudinal extension of this data-driven simulation, the structures they mapped exactly in the field of view of the receiver we used to show these observations. So one natural questions that we can ask is this only happening during June solstice? Oh, I guess not. And the reason is, for instance, over Brazil, if we were under low solar flux conditions, the vertical drifts during the early night times, they resemble a little bit those we see during June solstice. So it's more accurate to say that whenever we have this more flat behavior during the early nighttime hours, whenever we have a small contribution coming from geomagnetic activity, that can help the instability to start. And this is what I'm showing here. This is a case study for equinox, low solar flux. I'm showing also gold data here. So you can see in N01, no EPB was there. N03 EPB was there. N01, no scintillation at all. N03, scintillation reaching 1.2. And the only difference between these 2 nights is that in N03, we had some substorms. I did the same. I ingested the real vertical drift profiles on the Summitry, and again, we got coherent results. No geomagnetic activity, no EPBs. Small geomagnetic contribution, EPBs were there. So to summarize everything, these upward drifts during early nighttime hours, whenever they are not going really down after the pre-reversal hours, if we provide a small contribution from geomagnetic activity, that can be already enough to initiate the EPB. And that, I believe, is important to look at, because if we were to build any forecasting system, if we were on those conditions, the environment can change from a completely operational for GNSS users to an environment in which we have severely degraded GNSS signals. And I think that's all I have for today, and I will let you ask questions if you have any. Thank you.
We can have one short questions.
Sure.
Can you expand more on the logic that you used for identifying the bubbles from the quick look gold data?
That was a visual thing. I mean,
Oh, okay.
yeah, this is a very preliminary thing. Actually, I have a more sophisticated result that will be submitted soon. I'm just waiting for some feedback from the co-authors. But because that's kind of ambiguous, I'm using scintillation data now, because you have a better coverage in time, and you can ensure that you were in fact seeing something.
So are you using a magnitude or something to identify how strong the bubbles were? Like,
In gold,
yeah.
no, in gold was I mean,
Or
I
just
was relying, you
okay.
need to accept that I'm good enough to distinguish bubbles in the gold. I mean,
Okay.
by the power of faith. Yes.
Thank you so much. Thank you.
Thank you. Thank you, Prasan.
Let's thank our speaker again.
Thank you.
Okay, our next speaker is Dr. S.T. Bart from SRI.
Hi, everyone. I'm going to mention two events that we observed during the strong geomagnetic storms in last year, 2025 and 2026, when we saw the low latitude signatures of equatorial plasma bubbles in the as high as at 40 degrees north latitude. So the two events that I will mention are the January 20 and 21, 2026, and November 12, 13, 2025, focusing a little bit more on the 21 event here. So January 21, this is data from the Mango network of all sky imagers from, this is the red line or red line air blow, that is 630 nanometer. And this is a temporally filtered image where you can see the auroral activity in the north, but there is a significant bubble activity in the southern edge of the this conus coverage. So that is happening in the red line. However, what is the unusual part about this event is that we also saw, if you look at the green line, this is 55.7.7 nanometer wavelength. This is also a temporally filtered image. What you will see in a little while is the bubble coming, showing up in the green line as well, and this is about a 40 degree north geographic latitude. Of course, what you see here is not the actual height or actual extent of this of the bubble, because what we are learning is that what is happening is not so much in the at two different altitudes. Typically, the green line comes from 97 kilometer altitude air glow, and red line comes from 250 kilometer altitude or thereabouts. But when you look at both the okay, is it not working? Never mind. Oh, there. But if you look at both red and green line at the same location, what you see is the bubbles in the red line in the left, and the bubbles in the green line on the right, they look quite identical in the shape and structure and size. Well, shape and structure. So we are now working to figure out exactly what that height is. And the thought is that these are all coming from it's the same structure mapped across the altitudes. When you look at the swarm observation, actually, I think one of the slides is missing, but never mind. So Joe Huba has made a SAMI-3 model to actually do a simulation for this event, and what he's showing, which again, I think the updated slide didn't show up here, is a wedge in the altitude at magnetic equator, which is across all altitudes. We look at swarm data, and in the swarm data also you see a lot of variation at north of 35 degrees latitude, and the trough is very, very, it's in the mid-latitude on this particular event. The next event that I will not spend a lot of time on, but November 12 and 13, 2025, there was also another minus 200 DEC storm where we saw these are both green lines. The aurora in red line was so strong that we didn't see anything this bubble related. But if you look at the green line, what is unusual here is that you will, in a minute, you will see aurora in the north. The image will dip in intensity right there, and the bubble started, well, I'm calling it bubbles, but an unusual structure is propagating. On the next night, November 13th, I would like you to pay attention to the southern edge of this image in a little while. It will look nothing like an actual bubble, but it will look like wildfire. And so that is what we are trying to investigate now with the use of GPS TEC. In both of these events, we saw big ionogram traces which indicate presence of irregularities. We are trying to look at the actual strand TEC through the structures and trying to learn what is going on. So thank you.
All right, any questions? We can take 1 or 2 questions. All right, so for this one, it's from Texas. So
It's from Texas.
so it's the event when the aurora reached Texas.
Yeah, this is when the aurora will, in the red line aurora definitely reach Texas. The green line aurora you see in the northern edge, so it's not really reaching Texas, but it is very, very low latitude.
I see. All right. Any other questions? All right.
Of auroral origin?
I'm not sure, no. The wave train in green line, this? Unclear. That is north, up north. This is north to south, yes. Yeah.
All right. Thank you very much.
Thank you.
Okay, our next speaker is Gilda Gonzalez from UC Berkeley.
Good morning. I will try to do my best because I cannot see my own screen from here. Well, whatever. So, yeah. Today I will present results from a superposed epoch analysis of cosmic 2 IBM ion density data. This work was motivated by a previous one where we used ICON IBM ion density data, and we found that pre-midnight equatorial plasma bubbles were suppressed over South America during geomagnetic storms, but we did not observe the same effects over all the longitudinal sectors. So we decided to take a similar approach now, but using cosmic 2. These are the 3 scientific questions I want to answer. How geomagnetic activity affect topside EPV occurrence at post-sunset? Is the response longitude dependent? Does the effect change with disturbance intensity? To address that questions, we use the 6 satellites, the cosmic 2 satellites, for the period January 2020 to December 2025. To identify the bubbles, we use the sigma index described by Kieran Hillis, 1998. So a bubble was flagged when sigma was equal or higher than 0.5, and the density deviation was negative. We identify 125 events where the minimum sim age was equal or lower than minus 50 nanotesla, and as 0 epoch, we chose the time of the minimum sim age. For this particular work, we are only interested in pre-midnight equatorial plasma bubbles from -10 to 10 magnetic latitude. For context, on the left, I'm showing the monthly distribution of all the bands, and on the right, I'm showing the results for the superposed epoch analysis of CMH, BZ, EY, and AE. Unfortunately, I don't have enough time to talk more about this plot, so I will move on. Each of these panels shows EPV occurrence rate as a function of solar local time for different sectors. You have the global on the upper left, Asia, South America, and Africa. The gray line is the pre-epoch occurrence rate that I used 2 days before the zero epoch to calculate that one. And the black curve is the post-epoch occurrence rate. These are 2 days after the zero epoch. The red circle mark the bins where the difference was statistically significant. This means P was lower than 0.05. The main takeaway from this slide is that the post-epoch occurrence rate is lower than the pre-epoch one for the 4 sectors, and that the differences are statistically significant for almost all solar local time bins. In the upper panel, I'm showing the global EPV occurrence rate in colors as a function of epoch time and solar local time for a 5-day window around the minimum CMH. There is a clear color transition after the zero epoch from red to yellow. This indicates a drop in EPV occurrence just a few hours after the minimum CMH, and that later recovers gradually the subsequent days. In the bottom panel, I'm showing the number of observations per bins that were used to create panel A, and it's possible to see that the observations were mostly uniform. These plots are very similar to the ones I showed before, but here I separated the events on moderate on the left and intense on the right side. The main takeaway here is that the gap between the pre and post-epoch occurrence rate is more pronounced for the intense events. This is very clear in both South America and Africa. So to summarize, the main results of this work are that pre-midnight equatorial plasma bubble occurrence rate diminished after just hours after the minimum CMH and recovers gradually on the subsequent days, and that this decrease is more pronounced for intense events. I would like to emphasize that since I'm using cosmic 2, when I say that the EPV occurrence rate decreased, I'm talking about bubbles that reach cosmic 2 altitude. So maybe I have bubbles, but they are at lower altitudes. I'm not talking about that I don't have bubbles. I'm not saying that. Thank you.
Okay, we can take questions.
I have a question. What is the potential mechanism for this kind of suppression at the cosmic altitude?
I think it's the disturbance dynamo, maybe.
All right. Other questions? All right. If not, let's just thank speaker and let's proceed to the next. Oh, go ahead, Anna. Yeah, go ahead.
My question is, did you see any relationship with the, oh, thank you. How is EPB suppression if it was affected by the, I guess the UT of when the storm started, if that affected which LTs were suppressed versus magnified?
I'm not so sure if I understand your question. Are you talking about the UT time?
My question is whether or not the time of storm onset changed which longitudes were affected.
Well, for this particular case, since I only use it pre-midnight equatorial plasma bubbles, I'm just focusing myself on the post-sunset time.
Okay.
But I think if I have to think about it, I think it should affect. Right.
Thank you.
All right, thank you. Let's proceed to the next speaker. Next speaker is Yamina.
Okay, thank you. Good morning. I'm Shamila Melendi. I'm a PhD student at CEDAR, Argentina. And today I'm going to present my ongoing work about the impact for the Mother's Day storm over South America. I would like to thanks to NASA and SCOSTEP for providing me the opportunity to be here today. How can I pass with this? Touch, okay. So the Mother's Day event was an extreme geomagnetic storm during the solar cycle 25 that produced large-scale ionospheric disturbances. In this work, we are seeing these impacts over the Argentine sector and South America because it provides a broad latitudinal coverage. To do this, we use ground-based measurements and also satellite-based measurements, for example, ionoson, GNSS receivers, and all-sky imagers, and gold, Cosmic 2, DMSP, and SWARM. And our goal in this work is to characterize two structures over these regions. One is the equatorial ionization anomaly, and the other is the aurora lobe, and how they converge. In the middle, we can see two plots of tech. In this moment, we are seeing the main phase of the storm, and in the local time, it corresponds to the sunset and post-sunset time. In the here, in the first tech map, we are seeing an increase in tech values over Tucumán. This corresponds near 9 UT PM. And in the second increase, we are seeing this increase over Bahía Blanca, which is more south, and it's near 23 UT. In these four panels, we show the result of the ionoson data for the critical frequency of the F2 layer, and also the real altitude for this maximum frequency. These two correspond to Tucumán, and these two correspond to Bahía Blanca. And in them, we can notice a positive ionospheric response with values increasing respect to the quiet days. We also compare the Cosmic 2, that is the electron density versus the altitude, and we notice a decrease of the density values respect to the average days of the quiet conditions. This is a result that is showing an uplift of the F layer. On the other part, we have the electron density measurement by gold observations. In these maps, we notice two main structures. These ones have a V shape and correspond to the southern crest of the equatorial ionization anomaly. And in this part, we are noting an increase of density values correspond to the auroral oval. These values are moving first equatorward and then move back to high latitudes. Here we are showing an all-sky imager in Rio Grande, which is located here. And this image shows the red light of a brightness here over this region and correspond to the movement of the equatorward of this auroral oval. We compare these observations with the DES-MP, which measured the electron flux energy, and we are seeing an auroral precipitation during the same time of this main storm event. Finally, we compare also the ion density measurement by swarm. This is a pre-storm time, and we can identify these two crests of the anomaly. And for the short time, we notice that the southern crest of the anomaly moves over Bahia Blanca station. Okay. These values are increased respect to the previous value that we saw in the pre-storm. And okay, I think this is the time. So these are my conclusions. Thank you so much. And I invite you to visit my poster for further discussions. Thank you.
All right. All right, so thank you. So we can take one question, if there are any. Okay, if not, next speaker again, and let's proceed to next speaker. Next speaker is Ming Yang.
Good morning, everyone. My name is Mingyang Zhou. Yeah. Today I will talk about modeling the storm time post-midnight bubbles with semi-Suezcan mass. So semi-Suezcan mass, actually, you can get the results from the CCMC run request service. So yeah, the object is to understand the underlying physical mechanisms responsible for the post-midnight Victoria plasma bubbles during the 2024 May storm. So here we utilize a CCMC semi-3 coupled with wake-up mass. At CCMC, the wake-up mass is not very high resolution, so it's about like 1.25 degree in longitude and 0.94 degree in latitude. So this is not high resolution run, but we still can see bubbles. So in this study, I focus on understand the impacts of neutral winds, neutral compositions, and lower atmosphere forcing on development of plasma bubbles. So this figure just shows example of the neutral wind variations in the average during the storm time from wake-up mass. So the top panel just shows the meridional wind and zonal wind before the storm. So the bottom panel shows after the onset of storm. You can see very clear enhancement of meridional winds, also clear suppression of zonal winds. So we're trying to understand how these winds impact the post-midnight bubble development. So first is the storm-driven neutral wind, the impact. So this just shows the electron density. Left column shows the electron density as a function of longitude and altitude. So, and the right panel just shows the vertical equal speed drift. So before the storm, you can see that during the daytime, it shows very significant upward equal speed drift, at nighttime, downward. So it's a typical vertical drift variations. You also can see very clear reversal enhancement of vertical drift here, but there's no bubbles before the storm. And the second column here shows after the onset of storm, this during the main phase of storm, and near sunrise, you can see very clear development of superplasma bubbles before the sunrise. And the interesting is that if you compare the vertical drift with the quiet time condition, you can see that the nighttime vertical drift become upward, and daytime vertical equal speed drift become downward. So this is due to the disturbed dynamo electric field effects that cause this reversal of vertical equal speed drift. So this is also the main phase, you still can see very significant super plasma bubbles that penetrate to about like 2,000 kilometers high. And this during the recovery phase, again, see a continuous distribution of plasma bubbles. So, I also want to mention that you can also see here, these are post-sunrise bubbles that persist throughout the day. And I also want to mention that we also try to conduct semi-3 HWM and the wake-up mass simulations. That means we use the winds from horizontal wind model and composition from wake-up mass, but we do not see any bubbles. So this demonstrates that the neutral wind is very important, critical driver to trigger those super plasma bubbles. So the next, we are trying to evaluate the impact of neutral composition. So this is also semi-3 coupled with wake-up mass, but here we use the neutral composition from AMSIS, and then we can compare with semi-3 wake-up mass. So the top panel just shows the case 1 with wake-up mass composition and the winds. The bottom panel here shows the with composition from AMSIS and winds from wake-up mass. So the winds are the same, but composition are different. So here this shows the electron density as a function of longitude and the time at different days from the quiet time to storm time. But we just focus on these red rectangles. Here you can see that semi-3 coupled with AMSIS and wake-up mass, you can see a very clear continuous distribution of plasma bubbles, very clear plasma distributions. But in this case, semi-3 wake-up mass, this shows very irregular distributions. So next, we want to examine what caused this difference, why semi-3 wake-up mass shows irregular distribution of bubbles. So we examined the layer height, bottom side of layer height, and the E cross speed drift, and the Pearson conductance. So you can see that for the semi-3 AMSIS wake-up mass, basically, if we focus on this region, that there's no bubbles in semi-3 wake-up mass here. So you can see the conductance for semi-3 AMSIS wake-up mass is lower. And we also see very stronger vertical E cross speed drift and a higher bottom side F layer height. So this explains the difference why semi-3 wake-up mass, there's no bubble here, but here's just very significant bubbles. So this also demonstrates that composition actually can impact the longitudinal distribution of plasma bubbles in addition to the neutral wind variations. So the next, we want to evaluate the impacts of lower atmosphere forcing because we know that during the storm time, there are so many gravity waves, large-scale gravity waves, large-scale TIDs. So we want to know if those large-scale waves can trigger or seed bubbles. So again, we use the original wake-up mass wind. So this is the original simulations. At the right panel here, we use the post-process winds. That means we use the low-pass filter to remove all perturbations from below, including the large-scale wave structure, large-scale TID and solar terminal waves. So interesting that this electron density, you still can see bubbles. And the middle panel shows the vertical E cross speed drift. And the bottom panel shows the difference between the wake-up mass winds and the post-process winds, and the difference of the E cross speed drift. But interesting that if we focus on this case without perturbation, without waves, you can see very continuous distribution of plasma bubbles with very equal spacing. The spacing is very equal between bubbles. But in this case, that you can see the spacing is very irregular. That's because this atmosphere wave perturbation actually can induce E cross speed drift perturbations and then modulate the spacing between bubbles. So yeah. So this is my conclusions that we investigate the post-midnight bubbles during the May storm. So we find a neutral wind, storm-driven neutral wind, contribute to the midnight superplasma bubbles via disturbance dynamo electric fields. And the neutral composition also strongly modulate the longitudinal distribution of plasma bubbles by altering the Pearson conductance and the E cross speed drifts. And also we find that disturbance dynamos should be the primary driver to trigger the bubbles, but because we find bubbles still develop in the absence of atmosphere waves, but still, the atmosphere wave can affect the morphology and spacing of bubbles. So future work, we will try to conduct high-resolution simulations to understand the impact of medium-scale gravity waves on the storm time bubbles. Thank you.
We can take one question.
So your conclusion is that disturbance winds can create opportunities for creation of bubbles.
Yes, been a post-midnight bubble or post-sunrise bubble, because in these simulations, there's no penetration interference, because we use Weimar. So we focus on the post-midnight bubbles. So it still can observe, there's many observations showing that during the storm time, there are so many post-midnight bubbles and persist until sunrise. So we try to understand what caused those, post-midnight bubble.
So if Gilda's study that we saw earlier were analyzed for UTs or local times after midnight, she may have a different result?
Yeah, actually, I examined the cosmic 2 IVN density, and we define post-midnight bubbles, also post-sunrise bubbles. So it's just very clear, results. And there's also a paper showing that at the same case during the May storm, in Asia, they observed bubbles developed near sunrise and persisted until daytime. So I think overall the result is consistent with observations.
With storms?
The same storm, yeah.
All right, thank you. Due to the time constraint, let's proceed to the next speaker. Next speaker is Alano. Sorry about it. What's your name? Alano, okay.
The pointer and then we proceed with.
Hello, my name is Alana Cardenas O'Toole. I'm a graduate student at the University of Michigan, and I'm going to talk to you today about my work on the exploration of occurrence and energetics of equatorial plasma bubbles. So we used swarm in situ density data to develop a comprehensive detection algorithm to detect bubble irregularities. And from that, I'm presenting those results. I would love to show you the detection algorithm. It's at my poster, but we don't have time for that today. So right on this image, we have the percent depth, and that is the relative depth of the bubble compared to the background. Then we have the prominence, so that is the difference between the background density and the bubble density. So the prominence and percent depth both reached their peak before the F region fully decays pre-midnight. And then we can look at the relationship between the prominence and the percent depth to give us a bit more information about the evolution of the bubble and the ambient plasma density. So if we look at panel B here, we can see the normalized prominence and the normalized percent depth, and it's colored by local time hour. So we're able to see a little bit of a trend with different local times of what is going on. So we did that a little bit further. So in the bottom panel D, we have the slope between the prominence and percent depth as a function of, or between each other, and then per local time hour. And then the correlation is the correlation between the prominence and depth. So we can see that before 22 local time, the slopes are a little bit larger, and that may be a result of recombination in the background and in the bubble. Then as we go towards 4 local time, the background density reaches its diurnal minimum, and we start to see right after that, around 5 local time, an increase in the slopes and the correlation coefficient, possibly from the repopulation due to photoionization. We also looked at the bubble temperature. So on the top panel, letter A, we have the magnetic latitude versus the local time. You can see, hopefully, that we have a sudden increase in temperature between 4 and 6 local time, and it starts to decrease again towards 7 to 10 local time. So this is indicative of the morning overshoot that we see in the background. Additionally, we can look at the bubble temperature for the different solstice and equinox months shown in the bottom panels. So we can see that for solstice, we have an increase in temperature starting at earlier local times at around 4 local time, and then for equinox starting around 5 local time. Well, we believe that this is a result of pre-dawn heating, which we can look at in the top panel, letter B. So that is when we have the bubble is in darkness, the detection is in darkness, but the conjugate point is sunlit. So we're having photoionization traveling from the sunlit part to the dark part, causing heating in the bubble, and it would be earlier during solstice months because we have more uneven heating in the ionosphere at that time. So next, I'm going to talk about the change in temperature. So this is the bubble temperature. When I say bubble temperature, I mean the minimum point in the bubble, what temperature it is there. versus the edge temperature, so that's the half width of the bubble. So that is the change in temperature that I'll be talking about. So if we look at the panel B, we can see the medians plotted as a darker red points, and you can see that there is an increase right around 4 to 5 local time with a maximum around 6 local time. This is consistent with the results from Oyama et al. 1988, who saw something similar and saw a peak around 6:30 local time. The next plot shows the percent depth and the change in temperature. So we can see that as the percent depth, as the bubble is deeper, we have a larger change in temperature, and that is plotted as well when it comes to the slope of that between the two for each local time hour. And as we hit about 5 local time, we have an increase in the correlation. So in the morning time, it's a bit more related, the depth and the bubble temperature, the change in temperature. Additionally, we looked at not just morning and dawn, but we looked at pre-midnight and post-midnight. So that's the bottom 2 panels. So we have it as a function of magnetic latitude. And we can see evidence of adiabatic cooling from flux tube expansion. So as the flux tube, as the bubble starts to rise, there is a larger volume, and we have that adiabatic cooling. And then the ions and electrons start to fall down in a super fountain effect, and we see that heating. So if we look at the bottom panel here, we can see that there's more cooling around the equator, and then at higher magnetic latitudes, there's more heating. So this is consistent with results found by Huba et al., who proposed these different mechanisms. This study provides new insights into the physical and energetic processes associated with bubble dynamics, and I'm happy to answer any questions. Thank you.
All right, we can have one question. Any question? So the time is mostly quiet time or the active time?
So this is solar maximum. So this, I should have mentioned this. This was from January 2022 all the way through December 2025. So we have 4 years, so it's active and quiet, but the majority would be quiet because the majority of time is quiet.
Okay, thank you very much.
Thank you.
Okay, let's proceed to the next speaker. The next speaker is Benedict. Benedict, yeah.
Let's look there, I guess. This is not going to work. Oh, really? It's not. Oh, okay. Wait, it's okay. It's okay. Where's the mouse? Okay. Hello, everybody. My name is Benedict Pinheiro, and I'll be discussing gravity wave propagation through a quiet time, quasi-2-day wave disturbed atmosphere during a high equatorial plasma bubble event. So I'm going to come from the gravity wave perspective. We had a talk just previously discussing how they can affect the spacing and the morphology. So there are several sources of these equatorial plasma bubbles. I've listed some here. And at the bottom of the pyramid scheme, we have gravity waves generated in the troposphere. So that's what I'll be discussing and doing some modeling of that. How it kind of works is we have a figure on the left here where there's gravity waves that are generated from convective sources at the troposphere or in the troposphere. They make their way up. Sometimes they break and they can release smaller scale or secondary gravity waves, and they deposit momentum as well. They make their way even further up into the ionosphere, and then we have these large-scale wave structures which are similar to the gravity waves, which then are enhanced by Rayleigh-Taylor instabilities. This is the only equation I'll show, I promise, but the Rayleigh-Taylor instability growth is affected by the neutral winds, the the neutral winds, especially the zonal winds, make their way in several parts of this equation. And really, all these terms are coupled together, so it's kind of complicated. So instead, we'll just focus on wind variability at the lower atmosphere and how it affects the propagation of gravity waves, and thus the perhaps it contributes to the equatorial plasma bubbles. I chose a case study here, January 2015. This is based off of the Katrina Bossert's study, 2024. You can see here there's a sort of a wave structure in that image. Stronger plasma bubble. There was a lot of plasma bubbles that were recorded during this time, and the stronger ones were associated with the positive meridional winds in the thermosphere. The main, and in the red box, there was convective activity during that time as well. So there goes the convective source. And so how does the background atmosphere associated with the quasi-2-day wave modify the propagation of thermospheric and thermospheric impact of convectively generated gravity waves? For my model, I use a magic model because it can resolve small scales. So this is, we're talking sub 2 kilometers normally, so we can get up to 500 meters resolution, which can really resolve the small scale waves, and it's appropriate for it, and it could do it in a fast way. And the representative profiles I have, so we have these, one from HWM, which is solid black. We have one in dashed HWM, which is amplified to show the effects of amplifying the zonal winds. And then we have one from NavGem and combination with HWM for above 100 kilometers. The NavGem one has a stronger meridional wind, so that'll be of interest. And the source, this is just a Gaussian source, and you can change some parameters here. So you can change this is the storm, basically in math terms, but you can change the length of the storm, you can change the amplitude of it, so meaning the impact, you can change the size of it. So this is all done with modeling. This is kind of typical, especially with Gaussians. I'm going to go into the results because this talk is only 5 minutes, but this is what it'll typically look like. It'll be, just imagine a box and you slice through a box in the XZ plane, and you have a source here. The source is very tiny, and you just inject some energy into the atmosphere. I'm plotting winds here, or sorry, vertical velocities, so the vertical velocity of your fluid or your gas. So it starts off small, then as you get this density stratification in the atmosphere, it grows and you get these cool looking acoustic waves. And the XY slice you see here is these concentric rings, which are observed in TEC data, et cetera. As you get more into time, you get these gravity waves that propagate, the acoustic waves are done, and you get some asymmetry because of filtered gravity waves. But in the YZ, which is the top one, it's kind of symmetric because in this simulation, the meridional winds were weak. So they were allowed to propagate in one direction, but they were filtered out in the other one. Oh, no. Well, this was a cool looking graph, but we're going to skip it. What the heck? Oh, no.
Let's direct go to your conclusion, please.
Okay, I guess goes to my conclusion. We can't conclude anything. You didn't even see anything. So anyway, I can share this with you guys later. This was a failure. Sorry, guys.
Any questions first for him? All right, if not, sorry about it. And let's proceed.
Anna has a question.
Yeah, you do have a question.
This is a really interesting, some really interesting modeling results. So it looked, at least just to me, that sort of like you have like a perturbation and sort of have like almost like concentric rings coming out of it. From,
Yes.
Is there any magnetic field structure in your model, or is it purely fluid?
So this is a neutral atmosphere model, but the idea was to show the results from this to then put in as a seed for the ionospheric model, like Gemini,
got it.
for example.
Okay.
So I work with Magic, and then it's coupled with Gemini, so it'll just be one fluid motion to get to the ionospheric equatorial plasma bubbles.
Okay, perfect. Very interesting. Thank you so much.
Thank you.
Thank you. So next proceed to the next speaker. Next speaker is Fabiola. I'm present on behalf of the Jose Maria.
Oh, Jose Maria told me you will bring your laptop. Oh. Okay.
Try Command Q first. Probably need to bring back the PDF to the. Maybe we just follow the previous way.
Command Q somehow close the. Maybe we can go this.
But can't see it.
Sorry, the PDF does not work very good here.
We'll manage. Can you guys see the slides? Okay, so there's a little bit of an issue here. Let me see. How do I pass these slides now? Because I can't see them here.
The technician is coming.
My PDF does not work. You can scroll down.
Let me see. Okay. And how do I?
Do we need to see it on the screen?
I don't need. That's okay for me. I just want to be able to. Okay. Okay, guys. So we're gonna move from the model, and you see all the issues that the models have, at least when you try to present them. So that's why I'm an experimentalist. So there's no issues with that. There's still plots. So what I wanted to talk to you about today is you've seen some cases of EPB-like events that reach at mid-latitudes. We've seen them in the past few years, several cases of them related to the solar maximum. And what I wanted to talk to you about is some results that we get when we try to investigate how severe scintillation these types of events can cause. And I'm going to present you an example of what we call an extraordinary scintillation event that we observed. And more details on this paper by Jose Maria. He's the lead author on that study. Before I go into the results, I wanted to tell you a few things first. On the left-hand side, you can see a red line emission observations made by an airglow imager on Magnolia Observatory in Texas. It's a paper that was published in 2015 by Carlos Martinez of an event that was observed in 2013. And that paper they call super plasma bubbles. And a lot of people were skeptical about that event. There's a lot of discussion. There is a comment paper on that paper. There's a reply to that paper. And now we see them. We didn't want to call them super plasma bubbles. And now I can see everyone is calling them extreme plasma bubbles, super plasma bubbles. And I like to call them EPB-like events because we're still debating how these things are formed, if it's a combination of processes and things like that. That being said, I want also to tell you that I think we have enough instruments in terms of GNSS, low-rate observations over the United States, in South America and Central America that we can observe those events. When you can see those ROTI and TC maps very nicely. But in the past few years, about 6 years ago, I made a realization that we didn't have scintillation monitors over the United States, and they were expensive, and people thought that we didn't see scintillation over the United States very often that did not deserve to spend 15K on a scintillation receiver and distribute them over the United States. So what I did is I talked to my undergrads and my students, and we have been developing this low-cost GNSS-based scintillation and TEC receiver that costs about a fraction of the cost of a commercial system. And we've been developing, and I'm not commercializing them. I just do give them. They do different types of studies with them. If you went to the poster session, you saw them doing drifts with them, studying sporadic key layers and different things. And now I have folks that are citizen scientists trying to install them and work with them. So that was the goal. So once that got going, then we started distributing them in different places. We have maybe 30 receivers over the globe now. We have 12 receivers over the United States, but I don't have the time to go over the details. I'm just going to focus on measurements made by 3 receivers. That one was deployed at Jicamarca at the magnetic equator, another one in Costa Rica, 20 degrees magnetic latitude, and another one at UT Dallas. And what we're going to do is we're going to look at the scintillation that is observed by these receivers associated with this event right here, this EPB-like event that occurred in March 23-24 of 2024. So you can see the typical maps that you see in other presentations of this structure going from the equator, reaching mid-latitudes and moving eastward, westward, like some other folks here presented. And I'm going to show you, so the question was how much amplitude scintillation one event like this would cause. And this is what it looks like. So there's a couple plots in this slide. On your left-hand side is the map with the IPPs telling you how severe scintillation is for a specific time window in there. But what you see on the right-hand side are the time series of S4 indices for these 3 receivers. On the top, you have the receiver in Dallas. In the middle, you have the Costa Rica receiver. And then at the bottom, you have the Jicamarca receiver. And there's a few points that I wanted to point out. First, you can see severe scintillation over Texas, which is very not common to see, but became very common in the past few years with solar maximum. Okay, and that is in agreement with the observations that Carlos did back in the day in 2013. Now, in the middle plot, this event, what you see here is S4 affecting every single channel of my receiver. You can even see white spots on the bottom, on the background, saying there is no scintillation, there's no background levels anymore. Everything went up. The other thing that you can see from that plot is that you have about 10 hours of extremely intense scintillation on the signals, 10 hours. It goes into the day, into sunrise, and it lasts until daytime with moderate scintillation. The third point is the bottom panel here, that is the scintillation at Jicamarca. Jicamarca is located at the magnetic equator that you expect the scintillation to be weak because of the fountain effect and the low densities. Not only you see strong scintillation at Jicamarca as well, you see very severe scintillation in the post-midnight sector where you expect the densities to be even lower. So this is an extreme event that is associated with one of those super EPBs. My last slide is just to tell you the geomagnetic and ionospheric conditions associated with those. On the left-hand side, I have the DST just to tell you this is associated with a geomagnetic storm like the other events that you've been presented in here, is during the main and the recovery phase of that geomagnetic storm. What you have on the right-hand side are, in each row, you have TEC maps for 3 different days. The day of interest is 24, and you can see the densities on that day are much higher than the densities in the previous day and the day after. That gives you conditions for 2 things. It gives you the background density for a strong scintillation, and that's why we see severe scintillation in my measurements, but also remains very high for several hours. And that also keeps maintaining the bubbles alive and allowing them to propagate to very high altitudes, following some of the work that Mendilo and then Jonathan Kroll and Joe Huba did, that you need to have large background densities in the top side to allow those bubbles to reach very high altitudes. So that's what we saw. I don't have time to go to the details, but there is also conditions, interplanetary conditions, favoring the development of more plasma bubbles during the post-midnight sector, and that's why you see scintillation lasting until, daytime. I'm going to stop in here, and then I'm going to take your questions, okay?
We can take one question, Annie.
Hi, Fabiano. I have comment and question regarding a debate about whether these are super bubbles or not. I think now the community will accept the idea of super bubbles because they are connected to the lower latitude and they're much bigger than TIDs. So TIDs are kind of 0.1 TECU, but we're talking about multiple TECU perturbations. The question I have here is that in the slide 3 or so, the UTD scintillation was enhanced, but that was fairly short. In other times, it was kind of weak to moderate scintillation. Do you think there's a situation where severe scintillation like this low latitude scintillation can extend to mid latitude under certain conditions?
There's the first comment that Tosh made is that this consensus about this being an EPB that reaches those high altitudes, I think this is still open to debate. I think there's two processes that amplify, and we need to understand a little bit more. It seems like, I'm telling you based on looking at the data, that something seems like locally being generated and combined with bubbles. That's my perspective from an observational point of view. The second point is whether or not we're going to see scintillations that last longer than what we see on this example, and the answer is yes. And we have cases of that. We're processing the data, and we're going to be able to tell you that we have strong events that last longer than this. I do not expect them to last as long as the Costa Rica though, right? Because Costa Rica, what happens is you have the super plasma bubble, it reaches the mid-latitudes, and then the secondary plasma bubbles that are generated in the post-midnight sector, they don't have the ability to reach a high altitudes like mid-latitudes, but they still reach Costa Rica, and that's why you see that event in Costa Rica lasting so long.
All right, thanks. Maybe you can just talk offline. Thank you. All right, next, thanks speaker again. Next speaker is Anna.
Thanks so much. Hi, everyone. I'm Anastasia Newhart. I'm a research scientist at NOAA SWPC, and I just want to give you guys just a quick overview of some of the recent model developments we've done on our model, GLOTEC. So GLOTEC is a data assimilation model. It runs an extended Kalman filter, and we use IRI as our background data model. It does run a 3D electron density grid, though currently the only data products we're making public are the 2D results, since the full 3D results are sort of still work in progress. So currently, the model has been available operationally since February 2025, and you can view the current nowcast on the SWPC website. If you want to download GLOTEC data, that's available through NCEI. Currently, the data sources that we're assimilating are ground-based GNSS observations, since we only assimilate different types of TEC. So we're assimilating ground-based observations, and then also space-based from COSMIC 2. So currently, GLOTEC has the best performance at low latitude, since that's where we're having the largest data volume, since we're using COSMIC 2 data. What we're currently working on is adding new data sources into GLOTEC. A big one of those is commercial radio occultation data, and I'll show you that we have now a new experimental data product that uses commercial radio occultation data from Planet IQ. So Planet IQ currently, I think, well, they have multiple satellites, but currently we're using data from 2 of their satellites, which are called GNOMES 4 and 5, and they are in polar orbits. So that does give us some data volume over the poles in addition to COSMIC 2. So this is our
this is our new experimental data product on the on SWPC's testbed. So you can view our current nowcast using that includes the Planet IQ data. The other thing that we've added into this version of the model is that we've changed the ConOps a little bit. So here, if we look with a laser pointer, in the operational model, so the version available on the main SWPC website rather than on the testbed, we are running the model with a 15-minute latency. The problem with this is that for the radio occultation data, this is very limiting. Since not all the data has made it back down through the ground stations to be available from for assimilation. So with this new version, we are waiting 30 minutes instead of 15 minutes. And this gives us a much larger data volume available. And then we're assimilating a wider window for the radio occultation. For the ground-based data, data latency is not a big limitation, so we haven't changed the window for that. But anyway, if you're interested, please check it out. For this, you can both look at the current nowcast and you can download data files. For this, we still are only having the 2D data products available, but we're still working on the 3D data products to be available in the future. And I guess just as a last little addition during my short presentation here, I just wanted to say that at SWPC, we are working on developing a scintillation monitoring product. So in order to do that, we're trying to combine multiple data sources so that we can have a global picture of the scintillation that's currently occurring. So of course, probably the highest quality data source for that is high-rate scintillation data from atmospheric monitoring receivers, but the number of those receivers that's available can be very limited. So we're trying to also look at scintillation data from 1 hertz GNSS receivers, and then also use the data from like Cosmic 2, this is the bubble map, and from other radio occultation missions such as Planet IQ. So this is very much still a work in progress, and I'd certainly appreciate any feedback you guys have, and particularly any data sets that you guys might use in your own work that could be made available either possibly for use in the data product or for validation opportunities. So I think that's it. Thank you guys so much.
Let's take one question if there are any.
It's true. And here's the website if anybody wants to check it out.
Yeah, if not, let's thank the speaker. And
Okay, thank you.
feel free to check out the SWPC website. All right, next speaker is Mary on behalf of the SNEHA.
Can I use the
laser
pointer?
pointer? Yes. Okay.
Only a little tiny one, okay.
Because we have 2 screens.
Yeah, okay, all right. So this little thing moves around. Okay, you can see it. All right, so this is Sneha Yadov's work, and I'm reporting on it for her. And it it does something I really like, which is connecting tail flow bursts to other important phenomena throughout the entire system, in this case to the equator, but it connects to the equator where I don't know much, so I need feedback because that's sort of my area of ignorance. So this report is really on 2 events that occurred at approximately the same universal time during these 2 wonderful superstorms we had in 2024. So I'll show data from the October 2024 storm, but everything I'm saying about this event also happened during the other storm. So if you can see it nicely in TEC. You start my movie, we tested it, but I don't see it now. Oh, okay, great, thank you. Back to the laser pointer. Okay, so you see up here at the upper central US, this big event in the TAC, and let's see whether I can make it go again. Oh gosh. Beyond my capability here. All right, didn't get my laser pointer back. Okay, there it is, I guess it's good enough. See the event up here at the higher US latitudes? And then as it moves equatorward, it gets down to these R4 and R13 stations. See, if you look at these R7 and R3 ground magnetometers, which you probably can't see very well on the screen, whoops, you see a drop in the N component. That's the typical signature of what we call substorm current wedge, which really is a signature of a flow burst and an auroral streamer. So we got a beautiful onset of a streamer up here, and that event then started to move equatorward. But before that happened, if you now look down here, just equatorward of the auroral activity, as we see in the TEC, you see this tremendous at R4 and R14 increase in the N component by about 250 nanotesla. So you got the drop at the higher latitudes, typical thing which we call substorm current wedge, but just equatorward of that, the stations just equatorward of it is really nice. See this tremendous 250 nanotesla increase in the magnetic field. Well, that is what's sometimes called the reverse substorm current wedge, which is a signature of the partial ring current. So as a flow burst comes in from the tail, causing the streamer that causes this TEC enhancements, there's a buildup of partial ring current ahead of it. Okay, that partial ring current is what gives you the region 2 currents. That is the region 2 currents. And that gives you shielding. In this case, it's really extreme. So we got this extreme situation of partial ring current buildup and the region 2 currents, which shows dramatically as this 250 nanotesla increase in the magnetic field just ahead of it. And then as that flow burst comes down and crosses these R14 and R13 stations, then you start to see the magnetic field drop. Okay, so just like it should. If you look at the SMR index, it jumps by like 200 nanotesla at SMR 18, which is just this region 2 current increase. And if you go to the equator, you see this tremendous increase in the overshielding, right? Okay, now I'm leaving my field of expertise. So this is eastward electrojet, upward lifting of the ionosphere at the equator. Am I doing this right? And the thing that Sneha was really interested in is when this happens. Here's a quiet day on the night side with a swarm satellite, and you don't see any equatorial anomaly, right? Now, the events right about between these two passes, and just after that, you start to see the formation of very strong equatorial anomaly peaks. So she's suggesting that this tremendous overshielding electric field is lifting the ionosphere, and it's blowing over and enhancing the anomaly peaks. So you guys got to tell me whether that's means sense. She thinks it's really important, and it makes a lot of sense to me, but I don't know about the time scales. All right, this is just a pretty picture from this guy's Missouri skies who shows this event, the brightening of the aurora and the development of the streamers that are the signature of this tail flow burst over the central U.S. and that are making this all happen. So flow channel driven night side overshielding conditions, this happens a lot. Whenever you got these flow channels in the auroral oval, they cause this region 2 current, and they cause an enhancement of shielding. That's what causes shielding. And it can be really, really strong and affect the equatorial electrojet in general, but this is just a really strong situation. So the same thing happened for the two storms at the same time in universal time, coincidentally, at the same locations, observed by the same instruments. And to me, it says this GPS is really a good tool for identifying storm effects at mid-latitudes, like over the continental U.S., and the things that cause, strong magnetic field effects, and power line interruptions and all that within the U.S. So, all right, and it indicates the connection between the auroral processes and equatorial electrodynamics. Thanks.
Yeah, go ahead.
Larry, this is very important. We have seen the amplitude scintillation at that latitude where you saw this substorm TEC enhancement, a high latitude. But this is a storm time, so we cannot differentiate whether this is driven by the storm itself or substorm. So the question I have for you is, have you looked at the same kind of event during quiet time substorm event?
Yeah, and we do see the overshielding, but I haven't looked. I don't think
that's the current surge. I mean, dropping the magnetic field.
Yeah,
I mean,
I
that would
haven't
be
looked at it
nice.
in terms of the equatorial anomaly.
No, I'm interested in high latitude, not the low latitude.
Yeah, the high latitudes. This is typical. So this is, people have talked about this reverse electrojet, and we actually, that's really common.
Okay, so it
So
would be
that-
nice how much actually impact it has on, radio frequency propagation during quiet time substorm.
Yeah, it should then. I don't know anything about that. You do. Got to talk.
Well, I know, but if we coordinate that kind of observation during quiet time substorm, so we can take a look at the VHF or L-band scintillation, what it
Okay,
looks
let's
like.
do that.
Okay.
Okay, that's wonderful. That's just stuff I was hoping for.
Okay, thanks. Let's proceed to the next speaker due to the time interest. All right, next speaker is Mary Baus. Thank you, Mary.
Hello, everyone. My name is Marie Bast, and I'm from Embry-Riddle. And I just wanted to share some really exciting observations that we recently had at the Condor Meteor Radar Network. We're located in South America along the Andes. And also at this point, thanks so much to our collaborators for their help in making this work possible. So just to give you a quick overview of this network, let's see if this plays. Yes, so we have one central transmitter station and then 4 receiver stations that are basically spread out over the main ridge of the Andes. And we have an observing volume of about 600 to 500 kilometers, and we have data since 2019. And currently we're observing with 4 stations, soon to be 5, and we are routinely at about 100,000 meteor detections per day. And as Mesosphere people, we're very excited about the high-resolution, continuous, and 3-dimensional wind estimates. But before you guys kick me out of your session, I just wanted to share some more results that we had from looking further into the radar returns. So this is just one example event. It's an event that happened at the main station. And we basically, in the range time intensity plots, we see these very strong organized structures. They're very different from the meteor echoes. So those are just preliminary observations, of course, but these echoes appear on a pretty regular basis, often at nighttime. And thanks to the bistatic receiver configuration and the angle of arrival, they align with the expected magnetic field geometry. So if you look on the right, basically, we can see that they are very persistent. So we have this persistent signature at about 105 to 120 kilometers altitude, which is much higher than the typical meteor echo distribution that is more around 90 kilometers. And then also from the range, we can see that it confirms this very typical Doppler V signature. The analysis is still ongoing, but it appears that we're actually observing field-aligned E-region irregularities here. And now if we zoom out, since we don't have just one station, but actually 4, this gives us a super unique opportunity, because when we reconstruct these echoes in space, we can actually resolve the spatial organization and also the evolution of those irregularities across the field of view of our entire network. And so just to remind you, it's about 600 kilometers in diameter. And so basically the reconstructed Doppler velocities from those irregularities suggest that we're looking at large field-aligned structures, and they're moving through the observing region along the east-west direction. So you can see the 5 stations here, and this is all the same event for the 3 links. So those are the 3 latitudinally spaced stations that we had at that moment. And yeah, we're tracking them basically over several hundred kilometers. And we do see a lot of opportunities here to study these effects further. It might be useful for sporadic E and F region coupling, or if there's any model validation. So we would be very interested to look into this further. And just to zoom in on this very specific event, what's also super interesting is that there is a structuring that happens in altitude and longitude. If we look, there's like two different distinct populations here. The blue population is very localized in the east of the main Andes Ridge at altitudes of around 95 to 105 kilometers. And then the red population with the positive velocities is in the west of the Andes main ridge at altitudes of 100 to 110, so a little bit higher. We also have, of course, zonal and meridional wind observations from that time, and you can see that with the meteor detection rate we had in that time frame, we can actually go up to 105 kilometers and resolve the zonal and meridional wind at about 5-minute resolution. So yes, the cool thing about this slide is like this is all from one instrument. This is not, we don't need multiple instruments for this. So we're still looking into this. Those are very recent and preliminary results. And also, if we actually involve other instruments, so this is just to compare the scatter observations from the radar with an imager that is spaced at the right amount of distance. And we can actually simultaneously also observe F-region plasma bubbles and see the E-region coherent scatter here. So yeah, if anyone is interested looking into this, we would be very happy to collaborate if you have input or any additional data for that region.
Just one quick question. So measurements mainly occurs on day side, on the night side? 24/7?
Most of them are on the night side as of now. Like, so we don't have any statistics yet, but just from a preliminary look through the data set, it's mostly night side. All right, thank you.
All right, let's proceed to the next speaker, Mingjing from UT.
Hello everyone, my name is Mingjing. I'm from UT Arlington, and today my topic is impacts of E-region neutral wind shear on the equatorial plasma bubble development. So in this work, we mainly want to answer a question that can the large E-region neutral wind shears, large vertical gradient in the neutral winds affect the plasma bubble development, and if yes, which properties of shears matter? So to do this, we ran several numerical experiments using SEMI3, driven by the given neutral wind, temperature, and density. The first main result, we examined the orientation of the horizontal scale of shears. So from ICOM neutral wind observations, we can frequently see large horizontal scale shear structures. Most of the time it extends along longitudes, and sometimes they extend along latitudes. So which one matters? These two panels shows the maximum height that the equatorial plasma bubble can reach versus the local time. So on the left, it's the north-south case. The longer side band is along the latitude, and on the right is along the longitude. So you can see the blue line, the left one case. The height can be reduced by 50 kilometers, and on the right, it's almost identical to the default run. So this is because to satisfy the curve-free requirement of electric field, So roughly a narrow band along the longitudes will induce a stronger zonal electric field that will lead to a stronger downward polarization electric field plus electron accumulation near the bottom side of the F region, and together they will suppress the bubble development. And next, we examine the zona, the direction of shears, zona versus meridional. And on the top, we again shows the height versus local time. The blue lines is for the zonal shear case, and the green line is the meridional case. And on the top, the shear is set up at 120 kilometers, and on the right is set at 150 kilometers. The result shows the meridional shears have a minimal effect. This is because on the bottom, this is because the difference of the vertical current divergence driven by the zonal and meridional shears. For the meridional shears, the current is mainly carried by the Hall conductivity, and the Hall conductivity becomes very small at night. So this is why it has a minor effect. And finally, we examine the altitude. The altitude works through the conductivity altitudinal profile. Overall, the 100, if we set up the neutral wind shear node at 150 kilometers, we will see a minor effect. So this is because the Peterson conductivity above and below the 150 kilometers is more comparable. So that will drive a comparable but opposite current difference, and they'll cancel out each other. So this is a summary. The E-region neutral wind shears set up at lower E-region, like about at 120 kilometers, and the longer side extends along the latitudes, can mostly suppress the bubbles, and other cases have minor effects. Thank you.
So any questions? All right, so if not, next speaker. And next is the last speaker of today's session. So Deepak from CU Boulder.
Hello everyone, I'll be talking about some EIA crest, interesting behavior on the EIA crest during the recent storm that happened on 19 January 2026. Just to put things in context, on the left side I am showing a movie, how the EIA crest were behaving during the Gannon storm. You will see the South EIA crest is merging with the aurora. So it is a poleward, very clear poleward movement of the EIA crest. But in the recent time, in 26 January 19, on the right hand side, you will see that the EIA crests are getting merged at the equatorial latitude. Let me run that again. And this is the composite image of those two movies. Let us focus on the EIA crest behavior on 2026 January 19 on the right hand side. What are the observations here? We see that the equatorial ionization anomaly crests are well separated on the east of 45° west longitude, particularly over the Atlantic. There are a lot of like plasma bubbles which are crossing across the EIA crests, but on the west side over the South America, you see the EIA crests are merged. And notice that it is not exactly at the geomagnetic equator. It is little north of the geomagnetic equator, around like 5 degree north. So with that, let us see those 3 consecutive days on 17th January, 18th January, 19th January, how gold observes this behavior. On 17th and 18th, you will see well separated EIA crest, lot of plasma bubbles there. But on 19th, look at that east side of that merging. The EIA crests, you will find that it is little poleward comparatively to the 17th and 18th. That is one thing. The second thing, of course, the merging. So what is happening at that 45-degree west longitude? At that longitude, the sunset was crossing at time 21:15 UT on that evening. And with that, let's look at the geomagnetic and solar and ionospheric conditions, what is happening at that time. On the left side, I am showing the solar and geomagnetic conditions. The vertical dashed line here is the time 21:15 UT. Look at the IMF BG and BY. There is a strong reversal of BG from southward to northward and BY from eastward to westward. So this is triggering, this is expected that this kind of condition should produce oversealed electric field and which can promptly penetrate and create a downward equatorial vertical drift. And on the right hand side, I am showing the vertical drift over Hikamarka. The red is particularly on that day, others are in the previous days. And the EEJ, equatorial electrojet, over Peru and over Brazil, basically those 2 longitudes where we saw that merging. The EEJ shown here. And look at what is happening at 21:15 UT. Just after that, the vertical drift is getting downward and going all the way down. And we see the transition of the eastward electrojet is getting like westward. So this confirms, these independent observations confirms the westward EJ and the downward vertical drift. So this is the why we have observed that EIA crest merging happening there. And so with that, the take-home message from this unique observation is that unlike recently we have seen those superstorms, whatever has happened in 2023, 2024, 2025, in most of the cases we have seen the EIA, I think all of the cases, the EIA crest has gone poleward expansion, but this case, it is a very equatorial merging of the EIA crests. And of course, because of that, we don't see any plasma bubbles over those regions. And the reason is that the storm, along with the local time, how your sunset, where is the sunset terminator, and also IMF BG BY, that reversal for extend time almost for 5 hours, that is a crucial like unique feature about this storm which distinguishes it from the other storms. So if we didn't have these kind of observations, probably we will be in a particularly I was thinking before this storm that okay, why gold observation I am seeing all the time, it is a poleward expansion and merging with the aurora. And when we were discussing in our group, Richard, Wenbin, and we were discussing, probably it is that sunset terminator and how the interplanetary electric field, magnetic field is behaving during that time. And this event particularly shows that. So this is something great. Thank you.
So have you used some model to study more about this particular event? And also, have you looked into the neutral winds that might have caused the asymmetry in the peak? Like, do we shift it towards like one particular hemisphere?
Yeah. So first answer to your first question is no. We have not seen any model simulation. The second is I talked with people like who are the PIs of all the February interferometer for the winds, but I didn't get a good quality data set really to check. And
okay, thank you.
Okay, thanks.
Okay, go ahead, yes. Bring the mic.
Hey Deepak, nice talk. Actually, this is more of a comment. There is a paper by Abdu, I believe 2006, in which he shows something very similar to what you were presenting, this reversal in the vertical drift, which will probably will cause this kind of things that you were showing us.
Yes, I'll check that paper. And also I forgot to mention that in cold observation, we have seen this X pattern. I think you might have seen the X pattern in the EIA crest, the downward drift creates that. But important thing here is that how much that longitude extent that is happening. Here it is almost more than 35-degree longitude that merging is happening. So that is a very unique thing, but definitely models will probably give more answers. And yeah, so this is a very nice observations for the community. Thanks.
All right, thank you.
That's the end of this session. Thanks everyone. Thanks all the speakers. And we also have a AGU session with the same topic. If you find this session very interesting, please submit your abstract to our session. Thank you.